a variant, It's so good to restart these things. And today we have the pleasure to have Mary Powell with us for the first colloquium of the new season. So Mary is a PORAT postdoctoral fellow at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. She got her PhD at Yale in 2019, where some of us had the pleasure to meet her before. And she is particularly interested in the growth of supermassive black holes and how they co-evolve with their host galaxies. I could say many things about Mary, but she also paints beautiful portraits of pets. So if you have a pet, I strongly advise. Yes. I don't have a pet, but if I had a pet. Yes. And today she's going to talk about probing the halo scale environments of X-ray regions.
Thanks, Fabio. Yeah, it's really great to be here, especially in person. Today I'll be presenting the work I've done characterizing the host dark matter halos of including supermassive black holes by measuring the clustering statistics of Agn. So since we had technical difficulties this morning, the slides may be a little messed up because they're on this computer. But first, for some background, it's now known that supermassive black holes reside at the centers of all massive galaxies. And when these black holes grow during phases of extreme accretion, they're observed as active galactic nuclei, which I'm showing an example of on the right here, compared to a normal galaxy whose black hole is a central black hole is not accreting. So the very luminous point source in the center is powered by the central black hole. Supermassive black holes are 1 million to 1 billion times the mass of the sun. And unlike stellar mass black holes, these must have grown to their enormous sizes by accreting matter and merging with other black holes over cosmic time. So one of the overarching questions driving my research is how, when, and where supermassive black holes grow. How are they fueled? And under what conditions is this growth most efficient? This process is also extremely efficient at liberating energy, where 10% of the rest mass about is converted. And so AGN are also important because if a fraction of this energy efficiently to the surrounding interstellar medium, then it can have a large impact on the state of star formation in the galaxy. Several correlations between black holes and their host galaxies have motivated the idea that they co-evolve together. So one of these correlations is shown here, showing the global density of star formation in the universe. Here is a function of time with age of the universe on the x-axis. And the global star formation rate density is shown by the red dotted line and the data points. And also on this plot is the black hole accretion density, which follows the same trend. Both increased until around a redshift of 2, and then have been declining since. And between redshifts 1 and 3 is sometimes referred to as cosmic noon because it's at the peak epoch of both star formation and black hole accretion in the universe. This is one piece of co-evolution. Another important correlation is N-sigma relation, in which the mass of the supermassive black hole tightly correlates to the velocity dispersion of stars in the bulge of the galaxy, as well as correlating with the total mass of the galaxy as well. And so here, galaxies can have disk components that are star forming and rotation supported, as well as bulges at stars. And it's been found the black hole tightly correlates, especially with these bulge parameters. And the tightness of this relationship is unexpected, just due to the many magnitude difference of scale between the black hole and galaxy. So it has led to the idea that there's common sources of both fuel for star formation and black hole accretion, with both being possibly regulated by AGN feedback. But the details of these fueling and feeding processes are not well understood. So While there have been a lot of great work studying the connections between supermassive black holes and their galaxies, it's also useful to put black hole growth in a more cosmological context by connecting them to their host dark matter halos. And this is done by measuring how AGN cluster. So this provides independent constraints on how black holes and galaxies co-evolve over cosmic time, since the growth and evolution of halos is very well understood. So to explain more about this and to introduce clustering studies in large-scale structure, let's see if this video works. Okay, just very, very slow. But if it works, I'm trying to show here a visualization of extragalactic space. It's a fly-through of the Sloan Digital Sky Survey using real images of the galaxies as well as their 3D positions. And I don't know if you can notice it, but if it was working normally, you would, that the galaxies are not uniformly distributed in space, but they're clustered. They form bound groups and filaments with large voids in between. And the large-scale structures that these galaxies trace comprise a cosmic web of underlying dark matter that constitutes the majority of matter in the universe. So I guess you can kind of see it, but unfortunately, it's not as pretty as what it actually is.
Is that projector the problem?
No, I think she connected to the other computer there because your computer was not connecting well.
Yeah.
Mhm.
Okay, so these are snapshots from an n-body simulation of dark matter only, with time going to the right, where you can see that things get more clumpy as time goes on due to gravity growing the initial perturbations. These initial perturbations started out as quantum fluctuations in the early universe that were magnified in inflation. And since then, they've grown just from the influence of gravity. And it's at the peaks of this density distribution where dark matter halos collapse and form. So halos started out as initial overdensities that grew against the expanding universe. After reaching a critical density, they collapsed and virialized to form bound structures. Halos grow hierarchically by merging with other halos and accreting mass. And so it's at the centers of these dark matter halos where baryons condense into galaxies at the bottom of the gravitational potential wells that they form. So small halos may have 0 or 1 galaxy. The largest halos of 10 to the 15 solar masses compose hundreds of galaxies, each within their own subhalos. And subhalos are just halos that have fallen into the radius of the larger ones. So it's in this context that large-scale structure predicted from cosmology theory, which I'm showing on the left, can be mapped to galaxy distributions, which is what we observe on the right. And so by measuring how galaxies cluster in space, you can constrain their relationships with their host dark matter halos. And the same can be done for AGN. So how AGN cluster on all scales just depends on 2 things. First, on cosmology, which governs how halos cluster and how that changes over time. And secondly, on galaxy formation and evolution, which governs how AGN occupy their host dark matter halos. So the goal from AGN clustering measurements is to infer information about this while assuming cosmology, kind of working backwards from physics. Oh no, okay, you can't see that either. But for dark matter halos, their clustering strength depends on mass to first order at a given redshift. The box on the right is for some reason only showing the purple points, but there's also supposed to be others as well. But the point of this is to show that the more massive halos are more clustered than less massive halos. So by measuring the amplitude of AGN clustering on scales from 1 to 10 megaparsecs. The typical halo mass the sample resides in can be estimated with some assumptions in principle by knowing this mass dependence of the clustering. And look, larger scale environments of AGN is one thing that can be inferred from this. So the more clustered a sample is, the larger halos they reside in, and the denser their cosmic environments. So this can tell you whether AGN prefer living in cluster environments, like I'm showing on the right, or in the field where there's little galaxies around them. And knowing this can distinguish between various AGN triggering mechanisms. For example, galaxy mergers is one proposed trigger of black hole accretion. And they're thought to be most efficient in galaxy groups, where there's enough nearby galaxies to merge, but the relative velocities between them are not too high. And additionally, since halo assembly is very well understood, evolutionary scenarios of AGN can be tested by measuring the clustering as a function of various AGN parameters, like luminosity, redshift, etc. So for the purpose of this talk, what I'm focusing on here is which AGN parameters, if any, have trends with the clustering statistics. And so which ones, do any care about their larger scale environments? The quantitative measure of clustering is a 2-point correlation function, which is noted by WP. It's a function of scale, noted by RP. And it measures the excess probability that a pair of objects are a given scale away over a random distribution. So for galaxy and AGN correlation functions, there are 2 terms that dominate on different scales. On large scales, the 2 halo term dominates, which measures the clustering of AGN within separate host halos. And from the amplitude of this, you can estimate the halo masses that the sample resides in, as I mentioned before. And on smaller scales, less than around 1 megaparsec, the 1 halo term dominates. And this measures the clustering of galaxies or AGN within the same halo. So the clustering of the subhalos or the satellites within each direct halo. And this provides much more powerful constraints on how galaxies and AGN co-evolve or occupy their host halos. But because AGN are rare, clustering on these scales is less often able to measure with sufficient statistics. But doing so can provide lots of good information.
Sorry, can you go back to the former slide? Yeah, I wanted to understand what that actually, leader plateau referred to, because it seems like that there is a change in the actually a slope from, from smaller to larger distances. It's not kind of like intuitive for me, right? Like when you increase the distances, why they get a little bit actually, better correlated or less uncorrelated?
Do you mean this overall slope or the
No,
change?
it's the little bridge.
Yeah, exactly.
There's one point which is lower. I think Razi is asking about that.
Oh, here?
Yeah.
Well, so this is just the place where the different terms dominate. So the 2 halo term kind of goes like this. So it plateaus here, and the 1 halo term dominates at smaller scale. So it kind of starts here and goes up. So that's why the slopes change as a function of scale.
Okay. Thank you. Yeah, and then at the larger and larger distances, you would actually say that 1 halo term just doesn't work anymore, right?
Yeah,
Okay, I see.
it gets negligibly small. Yeah.
I see. Okay.
Okay, so there have been many previous clustering measurements of AGN in the past, from which the typical halo masses of the sample has been constrained by the 2 halo term clustering amplitude. So on this plot, I'm showing some of the measurements from the past 10 years ago, although this is a bit outdated now. But this is a function of redshift, where the color of the points correspond the different ways of finding AGN. And what's found is pretty independent of redshift, that the AGN detected tend to reside in halos of 10 to the 12 to 10 to the 13 solar masses, typical of group-like environments. But there are slight differences between the AGN selected in different ways. And it's important to consider how the AGN are selected, which objects are found, and which objects are missed for a given survey. Because the different AGN wavelength selection methods prefer finding AGN in different galaxies. So before getting a clear picture of how black holes are connected to the halos, these selection effects need to be taken into account and considered. So it's very difficult to compare clustering measurements from different surveys. For the measurements I've done, I've relied on X-ray surveys to find AGN. So to show the benefit of X-ray selection, I'm showing here a spectral energy distribution of a typical unobscured AGN. The accretion disk glows in the optical and UV, shown by the blue. The torus that surrounds the accretion disk glows in the mid-red, shown in red. And the area of hot electrons, very nearby the black hole, that come in upscatter accretion disk photons, are very bright in X-rays, which I'm showing in the light blue. So if you're looking through the torus, or there's a lot of gas and dust within your line of sight, obscuring the nucleus, then the SED would look something like this. Okay, like this, where the optical and UV emission disappears. The mid-infrared can be contaminated by the host galaxy emission, but the X-rays do remain, making X-ray detection one of the least biased and most efficient detection methods. It's been recently shown that obscured AGN are extremely common, so including obscured AGN in these samples is important because they're so common. So while X-ray selection is the least biased method, all are biased in some way. So what I'm showing here are just the distributions of host galaxy properties of AGN detected by different methods in a given survey compared to the overall galaxy population. And the point of this is just to show the histograms in each panel are all different from each other. And it's been shown that it's because each selection technique for each wavelength favors finding AGN in galaxies of different types.
You're seeing what you're missing of those populations
Exactly. Yeah.
using the different frequency methods.
Yeah. So the X-ray AGN are shown in green. They do a pretty good job at detecting things, but of course they're biased to high stellar masses, etc. So yeah.
Okay, so that is detected two ways. And then the inferred, have there been studies of the inferred galaxy host properties?
Yeah, so that's what this is showing actually. This is the same survey with multi-wavelength data, and they just compared the different samples of AGN detected by the different.
So this is all from the same survey?
Yes.
Okay, but just different selection criteria?
Yep.
I see.
Yeah. Okay. Looking at the dependence of luminosity on AGN clustering. Here I'm showing the previous clustering results from the literature again, but now as a function of luminosity rather than redshift. The color of each data point corresponds to the effective redshift of the sample. So most of these here reside in, or are in redshifts between 1 and 3, so around cosmic noon. And there's some indication here of a slight luminosity dependence of halos than the more luminous quasars. And one interpret, yeah,
You've been showing a lot of these plots. I want to make sure I know what's going on. So each of these points is from some collection of AGN.
yes,
Let us say 1 luminosity. You don't care what redshift, whatever luminosity you
Yes.
can get. You measure its clustering. And then you're somehow associating a halo mass with that,
right,
because you have some master relation between clustering and halo mass.
exactly,
And that comes from dark matter simulations.
yes.
Okay, and doesn't that have a evolution with redshift? Or
It does. So that's
Okay.
why you take the redshift into account when
when you
measuring.
do that?
Yes.
Okay, fine.
Yeah, so each point here corresponds to a large sample of AGN, all with different average luminosity, which is the x-axis. So one interpretation of this mild trend of luminosity has been that quasars may be more likely to be triggered by galaxy mergers, since the halos that they're associated with their clustering seem to be the halos that where major mergers are most efficient. But the problem is that most of the very luminous quasars are found in large volume optical surveys, while the low to moderate luminous AGN are found in X-ray surveys. So it's unclear whether the different host galaxy properties due to the different selections are causing this mild trend, or whether it is actually a global trend of AGN luminosity. So to bridge this gap, I measured the clustering of X-ray luminous quasars. So quasars that have luminosities around 46 or so, but are X-ray selected, to determine whether selection affects or luminosity dependence is what we're seeing here.
Sorry, and can I ask a question? That's kind of like related to what Ramesh asked, just to understand. So for this bolometric luminosity, how much you trust or even use the cosmological simulations? Is this the only actual properties of dark matter that you read them off from your simulation? Or if you have really cosmological simulation that also have baryons, can you trust a little bit actually their luminosities from Adrian there, or is actually it's not that much related?
Sorry, are you saying, can we trust the halo masses that we infer? Or
No, I'm just saying that.
These are all measured observations, the
Yeah.
volumetric velocities.
Yeah, but if you want to match those to some actually to
Oh,
someone, somebody in the cosmology.
I'll actually get to that later on.
Okay.
Because I will model AGN in cosmological simulations. So I'll compare the measurements to that theory. But ask me again if I don't answer your question.
Okay, but that's super relevant to what we are going to do anyway. Yeah, anyway, that's
Okay.
good. Yeah.
Okay. So to measure X-ray luminous quasar clustering around cosmic moon, I selected AGN in the stripe 82X and XMM XXL more fields. Just showing the footprints of those fields here. And the relatively wide area of these surveys, combined with the sensitivity, probes the more rare luminous quasars, but while also going to the redshift of 2. So I selected 2 bins of luminosity in this sample, measured the clustering amplitudes of each to get an inferred halo mass. And so here's the plot again, and here are my measurements shown by the red outline points. So we find a mild luminosity dependence within our sample, but it goes the other way as predicted, I suppose. And our high luminosity measurement is actually more consistent with X-ray AGN at the same redshifts than the optical quasars at similar luminosities and redshifts. So this suggests that the biases and the different wavelength selection methods are probably the cause for these slight clustering differences observed between optical and X-ray AGN, rather than a global trend with luminosity. But to further test this, I created mock galaxies with the same properties of this AGN post sample by forward modeling them in dark matter halo simulations for comparison.
Can I say a quick question?
Yeah.
So you're on the rightmost midpoint there, it does seem like it's a little bit in conflict with the green crosses.
Yeah, so
Which are optical, but then the cosmos is an X-ray.
yeah,
survey
you mean
too.
this point?
Yeah.
Yeah, so that one's at much higher redshift.
Oh, I see.
Well, like, yeah, slightly higher redshift. And at higher redshift, things are just less clustered. So it's a combination of the luminosity that you detect, but also the redshift that you're detecting. Two different things. But I guess the point was that this point is more consistent with this that has the same redshift rather than this that has the same redshift. Okay. So there are several different kinds of empirical halo models that can be used to model and interpret clustering measurements. These halo models are the map between the dark matter distributions and the galaxy distributions. So one type model is known as abundance match, subhalo abundance matching. And using this technique, a relationship between galaxy stellar mass and halo mass has been constrained. And it turns out that by itself, this simple relation can reproduce galaxy clustering quite well. So this is just an example of that. Oh, that's weird. Okay. Well, the trend is, the relation is shown on the left and on the right. I don't know why it looks kind of strange like that. But the black line is the prediction from this simple model. These are different luminosity bins of galaxy correlation functions. And the point is that the black line matches well with the data points. So you can sort of see there. So I estimated the stellar masses of my AGN sample using the multi-wavelength data available and created mock galaxies of similar mass to test whether AGN cluster consistently with comparable inactive galaxies. So the way I applied it in this case was by populating halo catalogs from n-body simulations. So I put a mock galaxy at the center of each halo and subhalo and assigned it a stellar mass based on the mass of that subhalo. So the galaxies at the centers of the host halos are centrals. The galaxies in the satellites are the satellite galaxies. Sorry, and the subhalos are the satellites. The mock catalog such that its stellar distribution matched that of the data. Measuring the clustering of this mock sample then tests whether the AGN cluster consistently with galaxies of the same mass. So the result of that is shown here this is the high luminosity bin of our sample. The correlation function of that is shown by the blue data points. And in the solid line shows the prediction from the mock galaxies, which shows that they're consistent, meaning that there's no evidence that luminous AGN reside in any kind of special environments, because they're consistent with what you'd expect given their host galaxy masses.
So was the distribution of halos in the previous slide just statistically generated?
Mm-hmm. Yeah. Okay. It's a large simulation. can statistically populate them. So, okay, so it could be that the selection at play here is just between the optical and X-ray samples, since in general, optical AGN typically are in slightly smaller galaxies just because you need a higher contrast between AGN and the galaxy detection. So it'd be interesting to do the same thing for the optical quasars, but it is very difficult to measure their masses.
So maybe I'm just missing the point here. This is a great confirmation that AGNs cluster exactly the way the host galaxies would cluster,
Yeah.
even without the AGN, right?
Yeah.
Whether the host galaxy has an AGN or not makes no difference to its clustering properties.
Right.
That's what you're
Yeah.
showing. And yet, I've been hearing for decades about feedback and AGN modifies the galaxy. Isn't this in a conflict with that? Shouldn't they?
Well, yeah, I mean, the point here is that, yeah, it's hard to, all this shows is that, it doesn't matter if the AGN is in the galaxy or not, they reside in consistent environments. So whether it's inconsistent with feedback, I'm not sure. But what this shows is that the host galaxy properties do primarily drive AGN clustering. You can't really infer triggering mechanisms and things like that from the amplitude because this is the main driver of it, and it hasn't really been taken into account before.
Okay. Yeah.
Okay, so while deep surveys probe the important cosmic noon redshift regime, wide and shallow surveys that detect AGN in the local universe.
Would that previous result then be interpreted as evidence that pretty much every galaxy hosts a black hole that is either active or inactive? And that from the clustering point of view,
That's right. And there's a duty cycle. Sometimes you don't see the AGN, sometimes you see the AGN.
right.
But on average, they're all doing the same thing. That's what I would take away
Yeah.
from that.
That's what I would as well.
Yeah.
But whether every galaxy hosts a black hole, you can't really look at the normal. The normalization is sort of averaged out with the clustering. So if you take a subset of it with the same clustering, it has the same.
Oh, it has the same.
Yeah.
So there's still the degeneracy with the occupation function.
Yeah,
But you
I'll discuss
the
that
duty
more though,
cycle and-
because later on I do model the AGN and take the space densities into account as well. Okay, so now going to Redshift 0, these surveys that detect AGN in the local universe can have much better statistics to further test what drives AGN clustering over a wider range of scales. So this is the SwiftBat Agn Spectroscopic Survey, or BAS for short. And these objects cover the full sky and are very hard X-ray sifted, meaning it's a very unbiased sample towards obscuration. The redshifts of these are all less than 1, so they're very local. And nice thing about the survey is that it overlaps with the 2-mass galaxy survey, which is shown by the black points here. And this is great because we can boost the clustering statistics by cross-correlating the AGN with this much larger and much denser sample of galaxies, and actually constrain the 1 halo turn as well as the 2 halo turn with clustering. So the first thing to look at with the sample again is to see whether these local AGN cluster consistently with the galaxy mocks in the same way with this better statistical sample and over a wider spatial scale range. So, okay. So measuring the correlation function of this sample is shown in the blue data points. And by the same method, I made a mock sample with the same mass distribution as this AGN sample. And again, it shows consistency. So the mock galaxy correlation function is shown by the dotted line. And even on the 1 halo scales, the clustering is consistent, meaning that AGN do cluster like inactive galaxies meaning there's no special cosmic environments for black hole accretion on average. So just the takeaways of this first section so far is that to first order, we find that X-ray AGN in the local universe, as well as at the peak epoch of supermassive black hole growth, cluster like inactive galaxies when controlling for stellar mass. And secondly, we find little or no evidence for a global luminosity dependence on AGN environments. And it's very difficult to compare results from many different surveys because of the different selection effects associated with each. But luckily, eROSITA is an X-ray telescope that is surveying the full sky in the X-ray band. And it will detect AGN across a very wide range of luminosity and redshift. So hopefully it will be able to break the degeneracies between luminosity and redshift and get a clearer picture of the dependencies of these. So more to come there. Yeah.
So just to make sure I understand this correctly, if you go to the previous slide, in a universe where, say, for example, satellites tended to have more AGN in them due to halo-halo interactions, and the one halo term would be a lot higher, and then you would see, okay, and then and then this is also not evidence that like ram pressure stripping is completely destroying AGN in satellites as well.
Right.
Or triggering them.
Right.
Right.
Okay.
All the favorite ideas.
Right.
On average, I mean, there could be special cases, of course.
Yeah,
So,
right.
Okay.
And cluster environments.
Yeah.
Right, these are not, these
Cluster
are field
environment-
surveys.
Exactly. These mostly probe
Yeah.
galaxy group environments on average. So
Were you expecting much of anything in the two halo term?
no.
Okay.
Okay, that's
Yeah.
I'm not sure if you're finishing up or,
No, she's finished half of it.
oh my God, okay.
We started late.
Yeah.
We keep interrupting.
Yeah, and in the next hour. So, let's just talk about spin for a minute. So if you're saying that the AGN cluster in the same way as the inactive galaxies, and that, and if one could say, okay, AGN have spinning supermassive black holes because they're more active or they have more energy extraction from the spinning black hole. Doesn't that say something about the evolution of AGN and non-AGN galaxies and clustering, because there are different modes of spin distribution over cosmic time?
I suppose if the spin has to do with the galaxy properties, if there's a connection between those, then you would expect differences there. But if the spin doesn't have to do with the galaxy, then it wouldn't say about that, because I just control for the galaxy mass.
I was just wondering whether you could work backwards to say, now I can say something about spin distribution over cosmic time in these different populations.
Yeah, I'm not sure. Is there any prediction with the spin based on the halo, dark matter halo, or the state of the?
No, I think there are no such connections. There are connections between, there are assumptions made about the
Right.
spin of the larger dark matter halo and that of the galactic disk, right?
Okay.
So of the stellar component maybe in the early stages prior to disruption by mergers and so on and so forth. But there isn't any direct connection between halo spin properties, galaxy angular momentum, and the black
And the
hole
black
spin.
hole spin.
It's just very different scales.
Yeah, I think that
Assuming
there is,
mergers would,
Construct everything anyway.
yeah.
and in fact, there is a very hierarchical, basically a scale between them. So for those that do cosmological simulation, I sometimes ask them just laughing, that's impossible to really actually go all the way down to, unfortunately, to the black hole spin. So I think even if there is something, we are unable to figure this out. So that's our inability, Of course,
yeah,
they should be related, honestly, but there is nothing that, there's no framework that we have so far. But those that they do GRMHG simulation, they have nothing to do with the cosmological scale. And those that are cosmological simulation, they have nothing to do with,
Razi.
Sorry about that.
All this will change in the next 4 years.
Really? Oh
Yeah.
boy. Okay.
Actually, that's
What's
the
going to happen in next 4 years?
We are going to be working at the PHI.
Oh, okay. I see.
All this connection.
But it's actually the benefit of empirical Halo models because it kind of bridges that, where you make some global assumptions, populate the Halo catalog, and you can compare with, the hydrodynamic simulations. etc. So I'll talk about that in a moment.
Yes, so let me finish my voice. So actually, regarding to the basically angular momentum of the galaxy and dark matter, it's fair to say that some of our analysis for the shape analysis in some particular simulations show that they're strongly correlated. In the sense that when you compute actually basically the shape of dark matter, that is the halo, and the shape of the stars, that is the galaxy, the baryons, you see that the minimum eigenvector of them, they are completely aligned or mostly aligned with the angular momentum of the galaxy, which is a good thing. So if actually Ramesh et al. can do a little bit further down to the scale, we are just all there, to make the
cool.
basically remaining connection to black hole. But yeah, that's
Yeah.
mysterious for now.
So that could technically be modeled and tested then if there's those global correlations.
Yeah, exactly.
That's
Yeah,
cool.
hopefully.
We should let Mary continue.
Yeah,
Yes.
please let me know if I'm like running out of time.
No,
It's okay now because of the delay in starting.
Yeah, we are
Yes.
taking into account also time dilation of the computers.
And the fact that, she's still all the way from Stanford.
Yeah, that's right, yes.
Okay, so next, using this rich, vast data set with this really good statistics and well-characterized AGN, I further investigated any trends, clustering trends with AGN properties, because it's those trends that can tell us much more about the underlying connections between AGN and their halos. So specifically, I'll now discuss the trends I found with black hole mass and obscuration and talk about what we can learn from those trends. Okay, so first looking at the trends with black hole mass. So we disaggregated the sample into 2 bins. On the upper left-hand panel shows the black hole mass versus redshift of our sample. And the blue points are our large mass bin. The red points are our smaller mass bin. And we chose the 2 bins in such a way that their redshift distributions match. I don't know why it's not showing the large bit, the large bin there and the redshift distribution, but they do. They're the same distribution. And because black hole mass measurements are uncertain by 0.3 to 0.5 dex, we eliminated that middle bin there to try to reduce the contamination between each bin of
So-
black hole mass.
Earlier you talked about binning the AGN by luminosity.
Mhm.
Here you're doing mass, black hole mass.
Yes.
You're not assuming they are proportional to each other.
Well, so I did this here because I wanted to look at sort of the more fundamental property of the
Yeah, but these
AGN.
mass determinations are from the.
Is it from the luminosity or is it a
Oh, sorry,
completely
no,
different?
no, they're from optical spectroscopy. So
Okay.
these are a combination of obscured and unobscured objects.
Mhm.
So for the unobscured ones, it's from the width of each beta line, the broad lines in the
Right.
spectrum. For the obscured ones, you calculate the velocity dispersion of the center galaxy stellar velocity, and then from that you estimate the black hole mass.
You
Yeah.
assume they lie on the correlation.
Yeah,
and-
yeah.
Yeah, but the people who have done this in the past, I think have generally found that all quasars AGM have Eddington ratio of 0.1 to maybe
it's actually-
0.5 or whatever. And so it's
With this sample, since we have these black hole mass measurements and obviously the luminosity function, the distribution of accretion rates and Eddington ratios
Yeah.
has been constrained as well. So we have the black hole masses and we have the distribution of Eddington ratios, and those are consistent with the luminosity function in the data.
okay, fine.
Okay, So measuring the correlation function of each here, of each bin. Oh, no. You can't, okay, it's not, you can't see it.
It's okay, describe in words. It's all right.
Okay, so.
You're doing great, actually.
So if you are able to see these correlation functions, they're consistent for the two halo term, but slightly diverged for the one halo term.
Okay.
Um,
Which one's on top?
The more massive black
Larger.
holes are slightly more clustered than the less massive black holes, which could mean that large and small black holes occupy their host dark matter halos differently. So, it's actually not a super significant difference if you can see it, but what this did motivate is the investigation of Agn Halo models, where the black hole correlates with the property of its subhalo, like halo mass. So instead of just comparing with mock galaxies, I empirically modeled the Agn and black holes in the n-body simulation, with the goal of explaining the difference that is seen in the data, as well as to constrain any potential relationships between supermassive black holes and their halos directly.
So when you do the large and small, what are the ranges?
The mass ranges?
Yeah.
So the low mass range is, between 6
6
and 7.5 or so, log solar mass. And the other ones, from like 8 to
8 to 8.
Yeah.
But I mean, isn't this clustering divergence for the one halo term just telling you that the mass assembly history of large black holes is slightly different from that?
Yeah, that's what I think it is. But I'll,
Yeah.
go into that.
Are the stellar mass distributions still the same?
They are slightly different.
Yeah.
So,
Yeah.
Okay.
but it turns out that that doesn't quite explain it.
Hmm.
Okay, so the method I used to empirically model the Agn in simulations was again using the forward modeling approach for full control of the selection biases. So I started with the halo catalog as before, assumed a relation between the black hole mass and the property of its subhalo like mass, and then assigned each an Eddington ratio drawn from the universal distribution of Eddington ratios, which has been recently measured by this in this data set. Black hole mass and Eddington
That is
ratio.
published. I would like to see that.
Yeah. It, I think it
Angelo,
just,
please find that paper. Yeah, I want to see it.
yeah, Team Anana put this paper on the archive like last week, I think.
Okay.
Okay, yes. So Eddington ratio and black hole mass determine the Agm luminosity. So forward modeling the Agn selection based on these luminosities produce Agn mock samples of Agn. And then the clustering and space densities of those mocks can then be compared to the observational measurements to check for consistency. So the idea was to use these three things, which are measured by the data, to say something about this. Okay, so for the Agn Halo model, I tested two different assumptions. In the first case, the only dependence on halo mass is through the black hole galaxy and galaxy halo scaling relations, with no other dependence on large scale environment for halo properties. And in the second model, I tested a secondary correlation where the mass of the supermassive black hole correlates with the halo property for fixed host stellar mass. And this was done by the method of conditional abundance matching, where each bin of stellar mass, you kind of assume that the most massive halos host the most massive black holes, the smallest halos host the smallest black holes. So forming a monotonic relationship between them, while also keeping the black hole galaxy halo relations in place. So to parameterize these models, I assumed the established galaxy halo connection and just vary the normalization, slope, and scatter of the black hole galaxy scaling law. And then to see if either of these models or both can reproduce the survey statistics. Okay. So this just shows finding the best fit parameters of the first simple case. The model isn't showing up here in the right-hand panel.
Oh, no.
But it does show pretty good consistency. So the posteriors of the best fit parameters are shown on the left. The correlation function, luminosity function is shown on the right. And it does very well at matching.
So well that you don't see the blue parts. They're exactly below the black parts.
I can
It's
show
so
you these
perfectly
plots
spaced.
later.
Turn your laptop for maybe it's
That's true. Okay, you can't, so the blue lines match the.
Oh, yeah.
You know, I'd say that the blue is just not working, but model.
But the
Yeah,
model
I
shows
know.
up, yeah,
Yeah.
I don't know what's going on.
Okay, and again, this is the second case where the black hole mass correlates with the peak mass subhalo. The best fit parameters for the black hole mass galaxy mass relationship are consistent with model 1. And again, it matches these two things very well. I can just show you here. The blue lines match the black hole.
So would it be right to say model 1 is a subset of model 2?
Yes.
So
yes.
model 2 is given more freedom,
Yeah.
but it
Yeah.
doesn't make a big difference.
Not in this case. They
Okay.
can both reproduce these very well.
These, okay.
But what's different about them is the resulting black hole mass, subhalo mass relationship, which is shown here. Oh crap, you can't see the scatter on it. If you look at my screen, model 1 has a much larger scatter than model 2,
Interesting.
which is unsurprising because in this case, you assume there's a correlation between the two. But it turns out that because of the very different scatter, different halo masses for the AGN are predicted. So in model mass of the resulting AGN loss produced by the model is 10 to the 12.4 solar masses. For model 2 is 10 to the 12.8 solar masses. And so these two models both predict the same clustering statistics and luminosity function, showing what the typical halo mass you get. So to see if we can distinguish between these two cases, we looked at what each model predicts for the trends with black hole mass clustering. See if this works. Oh no. Okay, I'll just show you my screen. I wonder if I can make this full screen. Okay, so the data is shown. Yeah, you can come closer. So,
We're so
okay, so the data is shown by this plot here on the left. These blue points are the more massive black holes, the red points are less massive black holes. The dotted lines is what model 1 predicts. So there is a bit of a difference between the two, but maybe not quite that much. And then this is what model 2 predicts, where there's a much greater difference between the clustering of massive versus less massive black holes. And model 2 is actually slightly more consistent with the data that we see here. Does that make sense? Can you all, yeah, can you see that? Okay.
So model 2, bigger black holes are clustering more.
Yes. So of course, we'll need more data to know for sure, to actually, distinguish between these models and see what that scatter is. But the good news is there are many next generation surveys coming that will provide similar and better statistics for these measurements. So not only will strain the local black hole mass subhalo mass relation, but we'll be able to see how it's established over cosmic time by constraining this as a function of redshift. Okay. So sorry you couldn't see that on the slide. But the takeaways of this section is that we've used the clustering and space densities of the vast AGN to constrain the local relationship between black hole mass and halo mass. We found that a model in which black hole mass correlated with the property of its subhalo, like mass, is slightly preferred over the simplest case, although future surveys can say for sure. But this could imply several things. It could imply that the most massive supermassive black holes formed in the densest regions, or they prefer halos that formed much earlier in cosmic time. It can also mean that black holes assemble ahead of their galaxies. So we'll have to wait till more data comes to see for sure, but it's kind of exciting for the future. And then lastly, the typical halo mass is inferred from the amplitude of the two halo term may actually be incorrect because it depends on that intrinsic scatter between black hole and halo properties. AGN do reside in a wide range of halo masses, the extent of which needs to still be determined. And other works have actually found this as well that have come out recently. Okay, so if I have time, I'll just spend a few minutes talking about the dependence on obscuration to motivate why this is interesting to look at. In the unified model of AGN, whether or not an AGN is observed to be obscured or not, this depends on orientation angle. If you're looking through the torus, then it is classified as obscured or type 2. Have a view of the accretion disk, it's unobscured or type 1. And so this model would expect no clustering differences between these two populations of AGN, since they're just the same objects viewed from different angles. However, it's also been suggested that obscuration is an evolutionary phase, where after a galaxy merger, gas and dust would funnel to the center of the resulting galaxy, fueling the black hole, but also obscuring it. But after some time, AGN feedback would do its work to clear out the surrounding gas and dust, making an unobscured quasar. And since this is an evolutionary process, you would expect clustering differences between the two. So these models can be tested by looking at trends with obscuration. So a few years ago, when I looked at this with the DR1, the first data release of, oh, sorry, I should also say that it's also interesting because previous investigations looking at this haven't agreed on whether they do cluster similarly or not. So I'm showing some of those previous measurements, and it really depends on the sample you're looking at, whether obscured AGN cluster more, unobscured do, or they have the same clustering statistics at all. And I think part of the problem is that many of these studies weren't able to control for other parameters. So when I looked at this with the vast sample, I split the sample into two bins of column density, but matching them in luminosity, redshift, and those galaxy properties. Just know that the distributions of the two bins are the same. Yeah, so of all of these different parameters. I apologize again. Oh, you can't see this one though. Okay, so after measuring the correlation function of each bin, we actually did find some differences between obscured and unobscured AGN on the scales of the one halo term, where it seems like obscured AGN reside in denser environments on smaller scales than the unobscured AGN, which would be inconsistent with the simplest unification models. Other things could be responsible for the obscuration besides the torus. If you're looking through the dust lanes of the host galaxy, that could be obscuring your line of sight. Or again, if there's a merger, that could be obscuring things. So I visually inspected each of these AGN, and I removed from the sample the cases on the right where it was clearly edge on or any kind of interaction or merger. And I found that, oh, it's interesting, you can't see this one, but you can see the other one. The clustering differences
obscured.
remained. Yeah, it's obscured. They were still had differences on one halo scales, meaning that it is circumnuclear gas that's obscuring line of sight in the sample and causing this trend. Okay. Well, after revisiting this with the new data, with updated measurements, the differences actually went down a bit. So there's still some differences in the one halo term. They're not as significant, kind of interestingly. But it was also found in this DR2 sample. Oh, shoot, you can't see that as well. I'll show this one to you. So it was recently found that high Eddington sources are more likely to be type 1, and low Eddington sources are more likely to be type 2s. So this is the two different Eddington ratio distribution functions for the type 1s and type 2s. This again is from Tanima and Anna's paper that was recently on the archive. And what basically shows is that, yeah.
They cross or the two, the red and the blue lines cross.
Yeah. So in this regime, the very low Eddington ratios, it's more likely to be type 2. In this regime, more likely to be type 1s. And this is consistent with the so-called receding torus model, where there's Compton thick and Compton thin gas surrounding the black hole. So this is a cartoon side view of the black hole torus system. And then past a certain Eddington ratio, the radiative feedback would clear away the Compton thin gas, reducing the covering factor of obscuring material. So since you're more likely to have a viewing angle through the torus in this low Eddington state, then these are more likely to be type 2s, and these likely to be type 1s. So to see if these different Eddington ratio distribution functions were causing the differences in clustering within our sample, I put the different distributions within the in the models that I discussed before to make mock type 1s and mock type 2s. Okay. And they do predict differences in clustering, but maybe not as strongly. So this shows the data. And then the lines show the mocks. And while there's differences, it's not maybe accounting for everything. So I guess the point of this is just to say that it's still unclear what the clustering dependence on obscuration is, whether type 1 and type 2 AGN reside in different environments or not. And this different accretion rates may be impacting why we're seeing differences, but maybe not accounting for everything. So this is still a mystery. Okay, this brings me to my summary. Thank you so much for being patient with this talk. We find that the clustering measurements are powerful probes of the linked assemblies of supermassive black holes, galaxies, and their host halos. We find that the first order X-ray AGN cluster like inactive galaxies at low to moderate redshifts. And selection effects are very important to be taken into account when interpreting clustering measurements in general. And we find that large and small black holes seem to occupy their post-dark matter halos in a different way. And this can be explained by correlation between black hole mass and host halo mass. And lastly, we find that obscured AGNs seem to reside in slightly denser environments in an obscured AGN, despite similar host galaxy properties. And so this is a mystery still to be determined what's going on here. Future surveys of different wavelengths and different redshifts, I think, will be illuminating. So thank you very much, and I'll take questions now.
Thank you, Mary. Sorry for the technical difficulties.
Right.